Alright, here's a problem I came across about a week ago on Reddit. Somebody was asking for help with this one. They stated that they had no idea where to even start, and I gave them a couple of ideas of my interpretation of the problem and just kind of gave them enough to get started and just left it for them to do on their own. But then somebody else, separate from the author of the post, commented asking for me to show my thoughts in more detail, and I told that person that it would be easier for me to explain it in a video rather than try to type it out over text. So that's what I'm going to be doing today. So it says, consider a 50 mile by 50 mile square area that has an existing fire somewhere within the region. As the fire manager, you must determine how many fire breaks to place. Each fire break is equally spaced as a cut fully from one side of the region to the other in a straight line 1/2 of a mile wide. The region between the breaks that is on fire is totally consumed but cannot spread outside that region. Examples of 1 and 2 breaks are shown below. Your job is to determine the number of breaks you should place to minimize the total area lost from the fire as well as the amount of area lost. Your solution should be clear and neat and include definitions of any variables you use, an explanation of any model you use, and a complete math solution as well as a full conclusion. So this thing is kind of an open-ended question. It doesn't strictly feel like a book problem. It feels like one of those sort of project problems that you see in some textbooks. So I have a couple of questions myself about how this is supposed to even be interpreted, and I even expressed those, I guess 2 different interpretations in my comment on the initial post, which is probably what prompted the other person to reply and ask me for a more detailed explanation. So let me go ahead and switch over to my document camera here. And let me just go over what I see in this problem before we attempt a solution. I'm probably going to do, let me see. So I don't know if I'm going to fully solve the problem using the second interpretation that I'm going to talk about, but let's talk about the 2 interpretations that I have. So first off, they tell us that the amount of area that we have to work with is a square of 50 miles by 50 miles, 50 miles by 50 miles. And we have these fire breaks, which are basically for example, you would have, let's say you dig up a river, or you pull out all of the flammable vegetation, all of the grass or something, so that if a fire starts, say, over here in the north area, and it starts spreading and it tries to spread south, it can't jump over here, so you minimize the damage because the fire in the north doesn't spread to the south, or vice versa. So that's the point of a fire break. Now this thing is supposed to be, they said, 1/2 mile wide. Clearly not drawn to scale here, but half a mile wide. What did they say? It doesn't matter. It's 1/2 mile wide and 50 miles long. So these fire breaks have a defined area. They have to be a certain width, because if they're not wide enough, then the fire can jump over that distance. So that makes sense to me that they should have a certain minimum width or length, depending on how you're defining width and length here. And that means that they have a specific amount of area. I'll say that the area for a break is 1/2 of a mile by 50 miles is 25 square miles. And then, of course, I should probably list the total area available to work with is 50 by 50 is 2,500 square miles. Okay, so it said your job is to determine the number of breaks you should place to minimize the total area lost from the fire as well as the amount of area lost, which is poor wording if you ask me. They should have said as well as the amount of area lost due to having them occupied by these fire breaks, because the idea is, like, let's say this is, let's say this 50 by 50 mile square is a city, for example, and if you create these fire breaks, then they're taking up space that could instead be used by, like, buildings and stuff. So you're rendering this area unusable, so you would like to not make too many fire breaks. Otherwise, the solution would just be to stuff this thing with as many fire breaks as possible, which would be, what, 100? Since they're each 1/2 a mile wide, you could fit 100 of them in there, which is clearly not going to be the solution, because otherwise you wouldn't really have an optimization problem here. So, yeah, you're trying to not use too many of these, but at the same time, you want to create enough breaks that if one of these areas catches fire, you don't lose too much to fire either. So that's kind of what you're trying to balance. And the way they drew the example of 2 fire breaks, they drew the breaks parallel to each other. So one interpretation of this problem, and I guess I'll draw a 3rd square for my second interpretation in a minute. So one interpretation of this problem is that these fire breaks always need to be parallel to each other. And I think this was actually the intended interpretation that you were supposed to have based on the example they drew, because if you really wanted to minimize the areas exposed to fire while not using as many fire breaks, it would actually be better to place your fire breaks in a sort of crisscross pattern instead. So I guess I'll go ahead and draw something. Let's say I have 3 fire breaks to work with. So it would actually be better to do one like this and one like this, and then for a 3rd one I would actually just put it on vertically like this. And that would actually minimize the 6 areas that are not occupied by the breaks a lot better than what I have here, which would be, let's see, 1, 2, 3, 4 areas. I guess I'll try and color them in. So that's 1 area, that's 2 areas, that's 3 areas. They're supposed to be equally spaced, but I was eyeballing it, so I couldn't really pull that off. Maybe I should have used a ruler, but hopefully that doesn't bother you too much. So I've got 1, 2, 3, 4 areas. If one of these areas catches fire, the other 3 are safe, versus over here I've got 6 different areas, and if one of them catches fire, the other 5 are safe. This would actually be the better strategy because of 2 reasons. Reason 1 is, well, you're segmenting your remaining area into smaller sections, which means if one of those sections catches fire, you're losing less to fire for a section of this size versus a section of this size. Let me actually try and do some math here just for just for the sake of actually proving it with numbers instead of just eyeballing it. So if I have 3 fire breaks here, then I'm taking away 75 square miles, and I'm also taking away 1.5 miles of length, leaving, let's see, so this was originally 50 miles minus 1.5 would be 48.5, right? That would be 48.5 miles. And if I divide that by, I've got 1, 2, 3, 4 of these regions, 48.5 divided by 4 is 12.125. So each of these sections is, again, not drawn to scale, 12.125 miles by 50 miles. So if a fire starts in one of these yellow regions, then I stand to lose 50 times 12.125 equals 606.25 square miles. Versus over here, let's see what I would have. So I would lose 1 mile from this side because I'd lose half a mile from one fire break and another half mile from another. So that's minus 1 mile, giving us 49 for this side, 49 miles remaining that are not used for fire breaks. 49 divided by 123, 49 over 3 is 16.333 miles. 16.333 after rounding. Versus, what's this going to be? So we had 50 miles for this north side of our square, minus half a mile for the width of a fire break, leaves us with 49.5, and then divide that by 2. We'd have 2 yellow regions across that length. So 49.5 over 2 is 24.75. And of course, if I multiply these, 24.75 times 16.333 is about 404.25. So this is about 404.25 square miles, which is about 200 square miles less than this. So yeah, just like I said, this would be the better strategy. And actually, it's better for another reason. Not only does it divide your, I guess I'll call it usable area, into smaller sections, reducing the loss from fire, but also it reduces the amount of area that you have to use for the fire breaks, because look at this overlap over here. So let me actually highlight in, let's do navy blue, this area over here and this area over here. That area, you don't have to dig up, or whatever it is that you do when installing these fire breaks, you don't have to tear down that area twice. You already dug it up or did whatever you had to do to prepare it when you installed the first 2 fire breaks. So if you were digging up rivers and filling them with water, you don't have to dig these areas twice. So you're actually saving this much area compared to over here. So if I did, let's see, we have 3 of these strips, and we said that the area for a break is 25 square miles. So in this example, we're using up 75 square miles used for breaks. Versus over here, it's actually a little bit less than 75. We'd have, I'll say that I wanted I'll say that I'm installing these two first and then the one that crosses through them. So if I install the first two brakes, that's going to be 25 and 25. That's 50. Plus, for this one, it's not going to be a full 25. It's going to be 25 minus 2 times, how much is that overlap area? Well, if these things are half a mile wide, if I know this is 1/2 of a mile, and I know this is also 1/2 of a mile, then I know these overlap squares are 1/2 times 1/2 is 1/4 of a square mile each. So each of those is 0.25 square miles. So that's 25 minus 1/2 is 24.5. So 50 plus 24.5 is 74.5 square miles used for fire brakes. I think this second interpretation is actually the smarter way to go about it, but it's also more complicated mathematically, and also if they really meant for you to do it this way, then I would think they would have shown that in the original diagram. Because if we look back at this, then it shows that they had the opportunity to crisscross when they drew that second drawing. If they had them in a sort of plus formation isn't the right word, but you know what I mean. If they had these things crisscrossing, then that would have been a more optimal solution, but they didn't go for that. So I'm guessing the intention of the writers of the problem was to just install your fire brakes all parallel to each other. So that's what I'm going to do, and then I'm going to get as far as I can with this more crisscrossy thing, which is going to be a bit more complicated, and I don't know if it's even going to be doable, but we'll see what we can come up with. But first, let's solve it for the case where everything is parallel, because that's the simpler of the two and probably is the intended solution. Okay, so we need to optimize, or well, I guess we need to minimize the total area lost. The total area lost is going to be area lost to fire plus area lost to installing fire brakes. So I guess I'm going to go ahead and write that here. A lost is equal to, I guess it's going to be equal to area of brakes. I'm trying to come up with a good name for it. I guess I'll just use brakes, plural, plus area of, I guess, I'll call it area of a region. And I need to come up with expressions for these. This first one is going to be really easy. Total area lost is equal to, for the total area occupied by brakes, each brake in the parallel case is occupying 25 square miles. So all I have to do is take 25 multiplied by the number of brakes. I'm going to call that n, to remind myself that this has to be an integer. We can't have like a fraction of a brake. Okay, that's all good. Now how do we get the area of a region? So when I have one fire brake, I have two regions. When I have two fire brakes, I have three separated regions. When I have 1, 2, 3 fire brakes, I have 4 regions. So it looks like the number of regions I have is always going to just be n plus 1. Number of regions, number of usable regions, whether they're used for buildings or farmland or whatever is equal to n plus 1. Number of fire breaks plus 1, at least in the parallel interpretation. Again, we'll leave this thing alone and mess with it later. Okay, and the area of a region then is going to be area of a region is going to be the total area remaining. I'll call it area remaining after you've installed all your fire breaks. Area remaining, did I spell that right? Divided by the total number of regions. And the area remaining is just going to be the total area, 2,500, minus the area that we lose to breaks, so that's the 25n again. Over n plus 1. So I can go ahead and copy that over to here. Area lost is 25n plus 2,500 minus, and I forgot to square the miles there too. Glad I caught that. Anyway, 25n plus 2,500 minus 25n all over n plus 1. All right, this is what we are going to call our objective function. If you've never heard the term objective function before, your objective function is the function that you are trying to optimize, whether you're maximizing it or minimizing it. In this case, we're trying to minimize area lost. So this is a function of an integer, which usually we can't really do calculus with, but we're going to assume that n is continuous for the purposes of doing calculus, and then we're going to have two choices between rounding up or rounding down once we get our optimal value. So let me go ahead and grab a new sheet of paper. I'm going to rewrite a lost as a function a of n, or I guess I'll call it a lost of n equals 25n plus 2,500 minus 25n over n plus 1. We're going to treat this thing as if it's a continuous function, even though it's not. And if I take the derivative of this and set it equal to 0, what do I find? A prime, a lost prime of n is equal to, well, that's going to be 25 plus, oh boy, this is going to be one royal mess here. Let's see. So it will be f prime g minus g prime f over g squared. I'll go ahead and take care of the g squared part over here, just using quotient rule. And f prime g, so top prime times bottom, so derivative of 2,500 minus 25n is minus 25 times n plus 1 minus g prime f, derivative of n plus 1 is just 1, times f is 2,500 minus 25n. All right, let's make some simplifications, and we want to set this equal to 0, so 0 equals 25, and then that's going to be, if I distribute, that's going to be, well, I'll have a plus here, and then I'll deal with everything else in the fraction, so that's going to be minus 25n minus 25 minus 25n minus 25. And then if I distribute the negative 1 over this, that's going to be minus 2500 and plus 25n. Oh, well, that's nice. The 25n's are going to cancel out over n plus 1 squared. Did I do that right? Let's see. Well, let me double check everything. So quotient rule, I did f prime g. Derivative of that is negative 25 times n plus 1. Okay, that's all good. Minus g prime f, so minus derivative of n plus 1 is 1, and yep. And did I distribute correctly? Minus 25n and minus 25, yes. Minus 2500 and plus 25n, yes. So I can indeed cancel these out. It wasn't too good to be true, unless I made a mistake in my double checking. But yeah, so minus 25 and minus 2500 is just minus 2525. And that gives me 0 equals 25 minus 2525 over n plus 1 squared. And I can multiply by n plus 1 squared throughout for the sake of simplifying. Or, actually, what I'll do is I'll add this over to the left-hand side. So that'll give me, let me switch colors. That will give me 2525 over n plus 1 squared equals 25. I can divide both sides by 25 just for the sake of simplifying. Or actually, I'll multiply n plus 1 squared over to the right and divide by 25 over to the left. So that'll give me 2525 over 25 equals n plus 1 squared. And if I divide 2525 by 25, then that will give me 2500 over 25 is 100 and 1. So I get 101 equals n plus 1 squared, square root of 101. Let's see, square root of 101 is about 10.0498, so I'll say 050. So roughly 10.050 equals n plus 1, which means n equals, if I subtract 1, it's going to be 9.050. Now, of course, we defined n to be an integer, so we can't have 0.05 of a fire break installed, so we've got two choices. Either we have to try out n equals 9, or we need to try out n equals 10. You might think that we should only try n equals 9 because it's the closest, but that's not really a guarantee in calculus. So let me see if I can illustrate this with a good example. If I was looking for, let me see if I can draw a graph where you could have either a rapid increase or a rapid decrease. Let's say, for example, how do I want to do this? Let's say, for example, that 9 is over here and 10 is over here. And let's say that you have area lost is let's see, so it would start pretty high at the beginning. So I'm not going to try and actually graph A of n, but I'm going to come up with some graph that starts off pretty high, decreases, and then eventually hits some sort of minimum and then goes up. So let's say I have a random graph that does something like this, and let's say that as it approaches 9, it starts getting pretty low, and you might think that, oh, well, because 9.05 is where it hits its lowest, that you should just use 9 instead. I think I already messed up what this was supposed to look like. So I'm trying to look for something where there is a rapid change. Let's say it dips down really far before it starts curving back up. Let's say it does something like that. Let's suppose you had a weird graph that does something like this. And let's say this point over here is your minimum, your 9.05, and you think, oh, well, since 9.05 is closest to 9, then the minimum must be at 9, when in reality, if you had gone to 10, you would have gotten this value, which is a lot closer to the actual minimum. So my point here is, don't be misled by the idea of closeness. Just because 9 is closer does not necessarily mean that 9 is where the minimum will happen. Maybe it will be. I wouldn't be surprised if that were the case, but my point is we do need to test both numbers. We do need to test both numbers. So let's go back and test 9 versus 10 and see which one of those gives us the lowest area lost. So I will switch to this lavender color for that. So if I do a lost of 9 versus a lost of 10, and I'm just going to rely on my calculator for this. 25 times 9 plus fraction 2500 minus 25 times 9 over 9 plus 1, so over 10. I get 905 over 2, which is 452.5. 452.5 square miles lost in total, versus if I do 10, 25 times 10 is 250 plus fraction 2500 minus 250 over 10 plus 1 is 11, and that's 454.545. 454.545. So it's really close. But alas, 9 wins out. You lose about 2 square miles less area with 9 fire breaks compared to 10, so 9 is the winner. We have ourselves a winner with 9 fire breaks. You lose 452.5 square miles overall, assuming that a fire starts in one of your yellow regions, your usable regions. Okay, so that's the base problem taken care of. Now let's take a look at the more complicated version of this problem. How on earth are things going to change now? Well, our objective function is going to be different, so let me actually grab a new sheet of paper and see what we can do with this. I'm going to go ahead and draw a couple of these square areas just so I can try and think about how I want to do this. So here's one, here's two. I'm probably not even drawing these the exact same size, but hopefully this will be good enough to illustrate my point. I probably don't even need 3 of them, but just in case. Okay, so let's see here. So I guess this is going to, first of all, the way I'm going to lay out these fire breaks, the way I'm going to decide whether to go horizontal or vertical, I think it should be fairly obvious that the optimal way to go about it is to install one horizontal, then a vertical, then a horizontal, then a vertical. So if you were installing 3 fire breaks, you would just do what I did over here, which is 2 horizontal and 1 vertical, or I guess you could also do 2 vertical, 1 horizontal. It's literally the same image rotated 90 degrees. So yeah, if you go 1 horizontal, then 1 vertical, if you keep alternating between horizontals and verticals, that would give you the smallest usable regions, the smallest of these yellow regions, and also it would maximize the amount of these overlaps, these regions that I shaded in navy blue that you don't have to dig up twice while installing your fire breaks. Well, dig up or treat or whatever it is that the professionals do when creating fire breaks, because like I mentioned, fire breaks can be just land that's dug out so that there's no burnable vegetation on it. It doesn't always have to be like digging holes and filling them with water, essentially turning them into rivers. But now I'm splitting hairs over details that are less important for the math that we have to do. Let me get back on track. So if I have, I guess the crux of the problem is whether we have odd numbers or even numbers. If n is even, then the way to go about it, you'd just get an equal number of horizontals and verticals. So if n is even, let's say I have 4, for example, then I would do a split like this. So there's 2 like that, and then I'd have 2 fire breaks like that. So that's if n is even. So n even. If n is odd, let's say for example I did 5, then I would do, I guess I would end up with 1, 2, and 3 horizontal and 2 vertical. And yeah, my lines aren't looking all that straight, but I think you understand what I'm trying to illustrate there. So what I'm going to do is actually define my area lost of n as a piecewise function. I'm actually going to write 2 different functions for area lost this time. So first off, I need to account for area lost due to just installing the fire breaks themselves. So just like I did back here, I started with the 25 square miles times the number of breaks. I'm going to have to write a modified version of this, which is going to be 25 square miles times the number of breaks minus the overlaps. And we already know how much area an overlap has. I calculated it earlier. Each of these overlaps, 1, 2, 3, 4, each of these overlaps has an area of 1/2 by 1/2, or 0.25. Area of an overlap is 1/4 of a square mile, 0.25 miles squared. So now it's just a matter of figuring out how many overlaps do we get given n. How many overlaps do we get? Well, for 4, I got, I guess we should say the number of overlaps, if you count your verticals versus your horizontals separately, I see that when I have 2 verticals and 2 horizontals, I get 4 overlaps. I see when I have 3 horizontals and 2 verticals, I've got 6 overlap regions. So the number of overlaps is just going to be the number of verticals times the number of horizontals. If n is even, the number of verticals and horizontals will be the same. It will just be 1/2 of n. So if n is even, for even n, we have 1/2 n times 1/2 n. Number of overlaps equals n over 2 times n over 2. But for odd n, that's not going to be the case. If n, in this case, we've got 5, 1, 2, 3 horizontal plus 4 and 5 vertical. If I have an odd n, then I've got 2 versus 3. So I guess in mathematical terms, I would define this using floor functions and ceiling functions, which you probably haven't heard of before if you just went from your classic algebra to pre-calculus trigonometry straight to calculus. You've probably never even heard of floor functions or ceiling functions. So basically, the floor function, sometimes on like online calculators, you'll just type the word floor and then put a number in. Floor of x equals x rounded down to nearest integer. And the opposite of a floor function is a ceiling function, which does the same thing except it rounds up. Regardless of how close you are to a lower integer, the ceiling function always rounds up. Regardless of how close you are to a higher number, the floor function always rounds down. So ceiling of x is x rounded, I forgot a d there, rounded down to nearest integer. And in textbooks that actually cover floor and ceiling functions, they're represented like this. Floor of x is represented like so, with the bottom, how do I say this, with the bottom extended. It's like square brackets, but only with the bottom side extended. And a ceiling function would be the opposite, with the higher part of the bracket showing. maybe in pre-calculus you were exposed to a type of floor function called the greatest integer function. And really, the greatest integer function is just a floor function. So if you've heard of the concept of the greatest integer function, that's what a floor function actually is. Except calling it a floor function, I think, is more intuitive because it reminds you that you're rounding down. And then that makes it really easy to tell what a ceiling function does. So greatest integer function is more ambiguous, which is why I don't like the term, but it is what it is. So I guess I can just do a couple of examples to show what this looks like in case it's not super obvious. If I do something like floor of 2.15, that's equal to 2. If I do floor of negative 3.7, here you have to be careful. You round down to the nearest integer, so that would be negative 4. If I do, let's do ceiling of each of these. If I do ceiling of 2.15, it doesn't matter that 2.15 is closer to 2 than 3. A ceiling function always rounds up. And if I do ceiling of negative 3.7, then that will round up to negative 3. Anyway, so what I'm going to do is I'm going to define the number of horizontals and verticals based using these floor and ceiling functions. So what I'm going to do is I'm going to take n divided by 2, and then I'm going to take the floor of n over 2, and that's going to be the lower number, the number of, I guess, verticals in my case, and the ceiling of n over 2 is going to be the number of horizontals. And let's test it out to see that it actually works. So if n is 5, then floor of 5 over 2 is equal to, well, 5 over 2 is 2.5, and floor of 2.5 is 2, versus ceiling of 5 over 2, 2.5 rounded up to the nearest integer is 3. So yeah, it's going to be floor of n over 2 times ceiling of n over 2 for the number of overlaps when n is odd. So where do I want to write this? I guess I'll write it down here. For odd n, number of overlaps equals floor or ceiling of n over 2 times floor of n over 2. It doesn't matter which order you multiply them in. 2 times 3 and 3 times 2 are the same. And yeah, I believe that is a pretty good definition for the number of overlaps in the even and odd cases. Okay, so now that I have these two descriptions for the numbers of overlaps, I can calculate the area lost due to installing fire breaks, and then we're going to take the actual sizes of these usable regions and figure out what they are in the even and odd case. So I'm going to do for n even, I'm going to have one function, and then for n is odd, I'm going to have another function. So for n even, the total area lost equals area of fire breaks for n even is just going to be 25 times n minus n over 2 times n over 2 as the number of overlaps times the area of an overlap is 0.25. So minus 0.25 times n over 2 times n over 2. I guess I can actually just simplify that as n squared over 4. Okay, so that's area lost to fire breaks minus their overlaps. And then I want to calculate the area of a usable region. I guess I'll shade those in yellow again like I did before. And let's see how I would actually go about calculating this. So we said earlier when everything was being installed in parallel that it was just n plus 1 for the number of usable regions, and I'm still seeing that in here, but along both directions. So I have, if I'm doing 2 fire breaks, then I've got 3 usable regions per vertical fire break, and then horizontally I've also got 3 usable regions per hold on, I lost my train of thought. I think you know what I was going to say. So I'm getting 3 by 3 essentially. I'm getting 9 areas 3 by 3. So I'm getting number of horizontal breaks plus 1 along this side times number of vertical breaks plus 1 on this side. So that would be n over 2 plus 1 by n over 2 plus 1 for the even case. That would be the total number of usable regions, and then to figure out the area of that usable region, oh boy, I can feel it. This is about to get really messy. So we've got the area lost due to the breaks plus, I think well, let's try and fit it in here. I think I'm going to regret trying to squeeze it in here, but we'll try. Plus area lost due to just losing one of these regions, the area of one region that we're going to lose to fire. We're going to divide by the total number of regions, which is n over 2 plus 1 times n over 2 plus 1. So n over 2 plus 1 squared. And then the total yellow area is the total area of the whole pink square, which was 2,500 again, minus the area lost to fire breaks. So copy this over. So minus parentheses 25n minus, I didn't even have enough room to fit it in. Yep, I knew I was going to regret this. 0.25 n squared over 4. Oh boy. And there's your a lost of n for n being an even number. Now, what about for n being an odd number? So for n being an odd number, we'd have 25n minus 0.25 times, well, I can't do n squared over 4 this time. Instead, I'm going to have to do ceiling of n over 2 times floor of n over 2. And I'm not going to make this same mistake again. I'm going to start writing it down here. Plus the area of one region. Well, the area of one region over here, it's still going to be the total remaining area after you take the fire breaks into account, so it's still going to be 2500 minus, and then in parentheses, 25n minus 0.25 ceiling of n over 2 times floor of n over 2, close parentheses, over, let's see, how many usable regions do I have? So I've got, it's still going to be number of horizontals plus 1 on this side by number of verticals plus 1 on this side. I've got 1, 2, 3 for 2 verticals, and I've got 1, 2, 3, 4 for 3 horizontals. So it's just gonna be ceiling of n over 2 plus 1 times floor of n over 2 plus 1. Oh boy. Ceiling of n over 2 plus 1 times floor of n over 2. I probably should have done this on another sheet of paper. Plus 1. And let me try to salvage this and make it a little bit more readable by just drawing a dividing line there. Yeah, hopefully that makes it a little bit more readable. Okay, and I think that's about as far as I'm going to go with this, but first let me actually justify what I did here. So ceiling of n over 2 plus 1 would just be taking your odd number, so in this example 5, divide it by 2, that gets you 2.5, and then take the ceiling of that, that would be your 3, that would be your number of horizontals in this case, plus 1, so that would give you 4. So for n equals 5, this would become 3 plus 1 is 4, and for n equals 5, 5 over 2 is 2.5, rounded down is 2, plus 1 is 3. So that would give you the number of regions per horizontal fire break, or sorry, per vertical fire break, I should say. So yeah, that would give you 3 plus 1 by 2 plus 1, or 4 by 3. So that is all checking out just fine. So I guess I really didn't need a third example over here after all. And yeah, like I said, this is about as far as I'm willing to go, because trying to do calculus on this is, I'm not sure how I can simplify this into a nice function and pretend it's continuous like I did back here. I think this you'd just have to actually throw into an equation solver and type it out and see what the optimal odd n is. This one you could still do calculus on. This, while messy, could still be treated like a continuous function, and we could do exactly what we did here, and that would give you the optimal even number. But for the optimal odd number, yeah, just use, I don't even know. I don't use Wolfram Alpha that much. I think I've only used it like 4 times in the past 10 years. So I don't even know if it has the type of functionality needed to do this. But you could very well just put this into, I think Excel spreadsheets can do a calculation like this, and you can just find your answer numerically instead of using calculus. Just or even on like the Desmos graphing calculator, you could do this. You could throw this into the calculator. It'll plot a whole bunch of points, if I'm understanding correctly, and you could just look at which of those points gives you the lowest value, and that would give you your minimum. So yeah, I think online calculators and equation solvers would be the way to find your optimal odd n. And if you're going to be using an equation solver anyway, you might as well use it on the evens as well and see which optimal n you have versus which optimal even n you have versus which optimal odd n you get, and then compare those two and finally decide which of them, the even one or the odd one, is the absolute lowest. But this, I think, has gone way beyond what calculus can do for you by hand, so I think this all but confirms that you were not intended to interpret the problem this way. But it's still very interesting, so hopefully it gives you something to think about, and hopefully you benefited from this whole reasoning process of how I decided all of these different I don't even know what to call them, formulas for determining numbers of regions and numbers of overlaps and all that stuff. It's more geometry than calculus, which is not a surprise to me. Pre-calculus is called pre-calculus for a reason. Pre-calculus is there to help you review your knowledge of algebra skills and geometry skills, which are definitely, in my experience, about 80 to 90% of most calculus problems anyway. But yeah, hopefully this has been helpful. I don't think I'm ever going to try and sign up for doing this again. Who am I kidding? I'm probably going to end up doing this again at some point because I have helpaholic tendencies that can't be, what's the word? That I can't get rid of. But yeah, I think I'll just wrap things up here and go ahead and take care of any final edits for this and upload it, and hopefully this will be a satisfying answer to whoever requested it. You're welcome, and hopefully other people who come across this video will also find it to be interesting. Take care, and I'll see you in the next one.